Today's activity is about uh, s- velocity and speed. So I'm going to write them down, or we'll say speed and velocity. And the equations really aren't really any different. It's sort of like this. Speed is just distance divided by time. So speed is distance divided by time. And of course, you could use this equation to solve for other things, like the way it is now. So the way this equation is now is I could tell you the speed of something if you tell me how far it goes, like the distance it travels divided by the time it takes. Okay, but you could also do distance is equal to speed times time. So in other words, times t on both sides to isolate the d. And this will tell you the distance something goes if you know how fast it's moving, the speed of it, and the time it travels. So this is how fast it's going, the speed, and how long it takes to get there. That'll tell you how far it was. And of course, we can use this equation too. So we're going to swap the s and the t here, and we get d divided by s. So in other words, time is divided by distance divided by speed. So how long is it going to take? That's the kind of question you would be looking for this one. How long is it going to take if I travel this distance and I'm going this fast? So that's the equation you would use if they're asking for how long it's going to take, and they give you a distance and a speed. If they're asking for how far did something travel, then they better give you the speed and the time, and you can just multiply them and get the answer. If they're asking for what was the speed an object was traveling, the average speed, you would just go, this is the distance it traveled divided by the time it took, and that's it. So that's speed. And this is a this is a scalar value. Scalar value. Just like distance was last time, remember? This one is a vector value, just like displacement was last time. Okay, so this is a vector value. So let's talk about velocity. Velocity is just equal to the change in position, which we call displacement, divided by time. It's the same equation. It's just that instead of distance, we have displacement. This is how far you moved from your starting position. So we went over that last week, how to find that. So if they want to say, what's the average velocity of an object, then you better know the displacement of it divided by the time it took to get that difference. Okay. You could solve for, just like you could solve for distance, you can solve for displacement. If I know the average velocity something traveled and I know the time, I can multiply them and I can tell you the displacement of the object. So this is the displacement of the object here. In other words, what is the displacement object if it was going 12 meters per second for 10 seconds? You know, so something like that. Then the last one obviously is the same. Oops, I got a little extra line there. So t is equal to, instead of distance, we have displacement, of course, and we divide it by velocity. So on this problem, you would hear in a problem something like, how long is it going to take if the displacement was this and the velocity was this? So they're really the same thing. They're almost interchangeably, except there is a tiny difference. Just like last time with displacement and distance, there was a tiny difference, right? One was how far did you move from your original position, and the other one was just the total distance you traveled. And you could just you just add them all up. There's no negatives or positives or nothing. You know, it's kind of like your watch or your phone or something that tells you how many steps you did, like a Fitbit. It just tells you how many steps you did for the day. That's this one right here. That's this one over here, the displacement distance, sorry. It just tells you how far you walked, the distance you traveled. It doesn't care whether you're still at home at the end of the day and you're like, man, you haven't moved at all. You're still at home. No, it counts every little step you did in the forward and backwards directions, counts and adds them all up straight up. Displacement looks at your where you started and where you ended. So technically, if you go to sleep where you woke up the same day, so you wake up and you go walking around town and go to school and do all this stuff, and you come back home pretty much every day, and I've seen like college professors give trick questions like that, like you know, a boy wakes up every morning in his bedroom, and at the end of the day he ends up going to sleep after a long day of walking and going to school. What's his average velocity? His average velocity would be 0. Give me a second, folks. I just need one moment. So here's the two differences. So if you look at any one problem, and by the way, today's problems, I have the answers on all of them. So obviously, I don't want to just see answers on sheets because I've already given you the answers. I just want to see that you solved for the answers, okay? So that's what I'm going to be grading you on, is whether you showed the work. Here's the answers. I'll give them to you. Just make sure you get the right answers when you're doing your work. So it says Sam is driving along the highway towards St. John. He travels 150 kilometers in 3 hours. What is his average speed? So we're looking at the stuff on the left, and pretty much it's just, if you look at my sheet here, it says what was his average speed. So we're looking at this equation here, and we just need to know distance divided by time. And it does give us the distance, 150 kilometers, and it does give us the time, 3 hours. So 150 divided by 3 is 50 kilometers per hour. And there it is, 50 kilometers per hour. So that's pretty much it. Let's skip down a few and just look at one other one here. Let's look at a tricky one. What is the average velocity of the Earth the instant it has traveled halfway of its circular orbit? Now that's like a hard one, right? Like, what is the average velocity of the Earth after the instant it traveled half of its circular orbit around the sun? That sounds hard, but really, if you just look here, folks, here's the sun. We all know how this works. The sun's here, the Earth is here. It will go all the way around, right? But they're saying after it gets halfway around the sun, right here, what is its average velocity? Well, remember, velocity is displacement divided by time. And here we go. We're looking at this. This is its displacement, correct? We don't care about it went all the way around. Here's its displacement. So what is this distance? Well, I don't know. I think we need to find out the radius of the Earth around the sun, correct? And then just times it by 2, and we'll know the displacement. So we could look up a radius of Earth's path around sun. Just do that. And it says it's 3,958 miles. Wait, that's not right. That's the radius of Earth. I was like, wait, it's way further than that around the sun. So let's see. Here we go. Earth orbits the sun at an average distance of 149 million kilometers. But it also gives you the miles. Which one should you use? Well, the cool thing is that I did give you the answer. So we're in meters per second. So we need to find out how many meters it is. So look up here, and we got 149.6 million kilometers. Let's go back here. 149.6 million kilometers. So how many meters is that? 149.6 million. Okay, kilometers. So let's just figure out how many meters this is first. So let's get rid of the kilo and make it into thousands. So 1, 2, 3. So 149,600 million meters. So I got rid of the kilo. I just converted it to meters. So it's million meters now. And then so let's times this by a million. And then so we're going to move it 6 more decimal places, 149,600. And we're going to move, here's the decimal place here, 1, 2, 3, 4, 5, 6. 5, 6, and that is the number of meters that this distance is right here from the radius of the sun. So let's times that by 2 in a calculator. So this is the hardest problem because we need to look stuff up, and we actually have to think a little bit. So I'm doing this one with you. 149,600, then 6 zeros, 1, 2, 3, 4, 5, 6. And we're going to times that by 2. And we get almost 300 million, I think it is. Let's see. This is the thousands. This is the millions. This is the billions. So 300 billion. Okay. So 300 billion meters. Let me just double check that. Did I do this original number right? I'm assuming I did. So thousands, millions, billions. It sounds like too much, but let's just do the math and maybe we'll be right. So 300 billion. Thousands, millions, billions. Yep. So that's the total distance, from here to here, right? So that's our displacement. So we already know this number. It's 300 billion. I think it's 302 billion or something, but it's fine. That's close enough. Oh, now we need to know the time. How long does it take to get there? Halfway around the sun. It takes 1 year to go all the way around. So it only takes half a year. It takes 6 months. So I don't know. There's different ways to calculate this, but we can actually we can calculate it. Let me show you one way to do it. One way is to calculate it. You can go, there's 365 days in a year, but it only takes a half a year to get all the way around. And that's how many days there are in half a year. Then we can times that by 24 hours. Cool. That's how many hours there are in a half a year. It doesn't look like much, does it? And then times that by 60 minutes. That's how many minutes there are in half a year. And times that by 60 seconds. And then we get that many seconds in a half a year. Not much, really, doesn't it? 15,768,000 seconds in a half a year. So we can type that number there. The other way to do it would just be to jump on, let's say, 1 second. Oops. Pull up Google real quick, and we'll say, convert 6 months to seconds. And we get to 1.577 to the 7th power. Yeah, and that's what I got too. Rounding this to 7 would be 5.77. So that's right. So let's type that in, 15,768. 15,768 seconds. Okay, so there we go. We got the total displacement, the distance from here to here, and we got how long it takes to get there. So the average velocity would be, let's do the math. Clear. And we're going to do 300 million or 300 billion. There we go. Divided by 15768,000. Enter. And I get 19.025. 19.025. And these were meters, and these were seconds down here. Sorry, that was seconds right there, not that one. And that's meters per second. Did I say 19? Why did I put 19 point? Why did I do that? Let's see. There was no point. It was comma, 19,025 point. Okay, so just 19,025. And what was the correct answer? Let's go to this. Oops, wrong page. $19,025. That's the answer. So that was the average velocity, because remember, the average velocity is nothing more than right here, the displacement divided by the time. So we take the displacement divided by the time and we're done. I mean, this one was a little trickier to find the displacement. They said it went halfway around the sun. So I need to find out the radius of the sun, times it by 2, because that's how far away it is. And then once I do that, I can put that number there finally. And then I just got to figure out how much time it took to get there and just convert 6 months to seconds, you know, on your own, or find a website to do it, whatever you want to do. And that's it, folks. I know there's not a lot of seconds in a half a year, but there's not a lot of seconds in your lifetime. The average person lives around 70 something years. I think 76 years is the average lifespan of a human. That's only about 3 billion seconds, around there. No, it's not even that. It's 2.4 billion seconds. 2.4 billion seconds. That's all the seconds you get to live on average. Some people get to live to like 3 billion seconds if you're really, really old. Unfortunately for me, I'm well over 1 billion seconds old already. So that means I am halfway done. Anyway, guys, so I'm going to sit here and wallow in my sadness, and you guys can